assignment or not. And remember, an assignment problem is actually a special case when it comes to linear programming method. Here we want to give some work or some job, maybe to a particular person, or let's say we transport the goods using this mode of transportation. Maybe we say our KCA bus, we assign it to route M. Another one, we assign it to route K. So you see you're assigning some work to be done. You're sending your work to, let's say, computer A, computer B, so that at the end of the day, you are able to have achieved a particular objective in your work. For example, you have an aim of maximizing your benefit, maybe the contribution or the return that to be made at the end of the day if, let's say, you are to deliver goods on time to a certain destination, or if that work is to be done by maybe a particular individual, then you end up having a return at the end of the time. So you are aiming at maximizing some benefit. Then let us assume you still want to, or you have another objective that you want to achieve at the end of the day. And this is, let us assume, you trying to minimize on the cost. When you assign the job, let's say, to a certain person, you want at the end of the day to have the lowest cost incurred. You minimize it to a certain level. So again here, we want to see whether that is achievable when we do the assignment. So what will tell me that the problem is on assignment? You'll hear of such words that, let's say, we want to give this work to ABCD. We want to have assigned, the word assignment will come out of the problem. And you can be able to tell for sure the problem falls under an assignment problem. So at the end of the day, you must have a problem which you're trying to address. But the problem is on assignment. Is it on maximization? Is it on a minimization? Once you have noted that this is a problem you have on the table, then you are going to find out whether your problem is balanced or not. How do you tell whether the problem is a balanced one or not? You'll be able to identify this by looking at the elements to be assigned. Yeah? So if those elements are equals to the number of assignments to be done, you say you have a balanced case. If for anything, whatever is to be assigned is not the same as the number of assignment, then we say the problem is not balanced. And therefore, what you do in an unbalanced case is that you first of all create a dummy. So at the end of the lesson again, we want to understand, do I have a balanced case or an unbalanced case? I've repeated this. A balanced problem is where whatever are the things to be assigned, they are exactly the same as the number of assignment. For example, I have 5 lecturers to be assigned to 5 units. Such a way, I'll assign under the basis of what we call one and only one basis. One lecturer taking 1 unit. Yeah? And here we are talking of a balanced case because we have 5 lecturers to be assigned to 5 units so that each one of them can actually take only one and only one unit, for example, to deliver to the students. If the problem is not balanced, for example, we could be having now the number of lecturers are 4, and the number of units to be assigned, or rather to be taken by those lecturers, are actually 5. What does that one mean? We have a deficit, and this is a case where we call it an unbalanced assignment problem. And what do you do in such a case? You create a dummy lecturer. A dummy is usually a situation which is imagined. So if the deficit is on the side of the lecturers, you create what we call a dummy lecturer. We are saying this if I have, let's say, the assignment to be done on the basis of, we have the number of lecturers here. Let us assume these lecturers are going to teach some units. Let's say these lecturers are 4, but the number of units, the courses here to be taught, the number of units to be taught by these lecturers are going to be, let's say, 5 in a school setup. So this is what we call an unbalanced case. They are not equal. They are not equal. So what do? We come and create a dummy lecturer here. But remember, if it is a dummy, this is not a real case. So such a lecturer will give us what? A return that is 0 if it is above the cost. Again, it will cost us nothing. Yeah? So you create an unreal lecturer, so that at the end of the day, that kind of a dummy so created will also be assigned a unit. Though in reality, that is just but an imagination you are actually going to have. So if the problem is balanced, assuming here we had 5 lecturers and the 5 units, they are actually equal, then we say our case here is already balanced. There's no need for us to create a dummy. In many scenarios, you'll find that the number of elements to be assigned are just but equal to the number of assignments. And what you do in such a situation, you go ahead and start working on how to do the assignment, following what we call the Hergelian Rule as you do your assignment. So in my document that I shared with you sometimes back, the assignment problem, once identified, you'll have to note, am I maximizing or am I minimizing? And I want us to note that if the case is on maximization, that is another special case. I've talked about a special case where the problem is not balanced, so you create a dummy depending on where the deficit is. Number 2 is a case where you have a maximization problem, and such a maximization problem, how you deal with it is first of all to convert the table to look like the problem was on the minimization. And so you are taking the highest value in the data given inside the table, you subtract all the others from such a value, including itself, and you'll have converted the problem first to be on minimization, then you follow the Hungarian procedure until you're able to do your assignment. Number 3 is a case where you are restricting an assignment on a certain route, for example. We normally call it an infeasible route, yeah? And this is a problem where you may find maybe the cost of, let's assume you are assigning our school bus to transport goods to Kisumu. We may restrict our school bus from taking such a route because maybe to us, the cost of assigning such a vehicle to transport the goods to the region would be too high. So in return, you'd want to avoid such an assignment. Maybe there's another vehicle by another company that if it were to take the route to Kisumu or to another region, the cost will not be so high. So you can allow such another maybe vehicle to take the route. So in the assignment, you would want to restrict, yeah, the element from from being assigned to such a particular region, and therefore it is a special case where we normally call it an infeasible route. And here you just assign a very big cost to the element, or you can just call it an unknown. In my illustration, the example given, I've used an X, which you kind of cancel that particular route, that at the end of the day, you avoid completely assigning the element to such a route. And lastly is a case where maybe the kind of an objective you want to achieve is not directly linked to your transportation or the cost itself, yeah, when it comes to the assignment. So if you're not aiming at minimizing and you're on maximization, remember first of all to treat the case as if it were on the minimization problem. So those are some of the items that I wanted us to just have them picked from our document. And if you are keen, follow up my my examples that I've demonstrated on that particular document. You'll be able to understand exactly what we mean by each and every area. However, whichever the problem, is it a balanced one? Yes, I use the Hergelian method directly in doing my assignment. Is it on a minimization? Yes, I use the Hergelian method directly in up to a point where I can do my assignment. However, if it is on maximization, first of all, you do the conversion of the problem to that of minimization, and you again follow the Hergelian method into doing your assignment. And later on, you'll be picking the original values that were provided as under the original table on the maximization as you do your assignment. But the point is, you must use the Hergelian method to solve your case. If it's a case of the infeasible route again, once you have assigned that big value, we are calling it X. X can take any big value and choose a bigger value than whatever will be provided in the table. Again, you must use the Hergelian method. Once you have confirmed that the problem is now balanced, there's no dummy that is being introduced, or you have already introduced it, you again go straight and apply the Hergelian method. So I want us to look at these steps under the Hergelian method, which allows us now to solve a problem in case of a minimization problem. How do we do this? Step number one, you have already drawn your table, okay? You have the columns and the laws defined. Usually, if you can have the assignment, whatever is to be assigned to, being put law-wise, so that where you're moving to, you have it as a column, the better. So you have already structured your table. You have the columns, you have the laws, and I suppose we know what are the laws, what are the columns. I keep on drawing this for my students, for you actually. So these are our laws, horizontal, and then we have the columns, vertical. In each and every column, in each and every law, we want to achieve one thing, what we call a zero in each. Column-wise, law-wise, at the end of the day, we have achieved a zero. So that when it comes to us closing those zeros, then we start by first of all achieving a zero in every column, in every law. So once your table is set, you come into it and identify the smallest element in each column. And you can as well start with a law. It doesn't matter whichever you start with. And how we do this, we are going to subtract that smallest element, yeah, from any other element in the law or even in the column, depending on what you have started with, including itself, so that you'll have created a zero somewhere in that particular law. You can as well start with the columns. If you pick a particular column, you have identified the smallest element in that column, you have subtracted it from every other element in the said column, and you are doing this including itself, you'll have achieved a 0 somewhere in that column. But you might have done this. Let us assume our case we started with columns. So we have subtracted every other small element from all the other elements in each and every corresponding column, okay? But there's a law that has got no 0 in it. What do? You do the same. Identify the smallest element in that particular law, subtract it from all the other elements, including itself, and you'll have achieved a 0 in that particular law. But for a law that you already have a 0 because you started with the columns, don't distort that. Actually, you don't do anything in that particular law. Once you have achieved a 0 in every law, in every column, you now start covering those zeros. You draw some lines which will be closing those particular zeros. And you start by closing as many zeros as possible in a particular law or in a particular column. Again, it doesn't matter. You can opt to go column-wise first and then law-wise, or the vice versa. And as you do so, you are drawing a line that can manage as many zeros as possible. Once you have done so, you ask yourself, are the number of lines covering the zeros the same as the number of assignments? For example, in our demonstration area, we had 5 lecturers to be assigned to 5 units. Whether you created a dummy or not, the case was 5 lecturers, 5 assignments equals to the number of units to be taken by those 5 lecturers. But now after you have drawn your lines, you realize that the lines are 4. The number of assignments were 5. The solution is not optimal and you cannot go ahead and do the assignment at that stage. So again, you actually go back to your table already achieved and you identify a particular uncovered element in the whole table, which is the smallest element in that particular table. Such a way you'll subtract it from all the uncovered element in the table, including itself. But if you find there is a covered element by only one line, you don't interfere with it. However, you might reach to a point where the covered element is actually having a point of intersection, meaning it's being covered by more than one line. So what you do, you add that uncovered element, remember the smallest, to the point where there's an intersection between some lines. And therefore, you repeat the same process up to a point where you have covered all the zeros, okay? Count the number of lines covering the zeros, and if let's assume this time round, they are now equating to the number of assignments, you go ahead and you do your assignment. And then you can go back, you find out, was my objective on minimization or maximization? If the objective was on maximization, then you must use the original table that was given before you convert it into a minimization problem when it is at the point of now doing the assignment, so that now it will line up with your major objective. If the problem was on minimization, you directly pick the figures from the original table, and once you have done the assignment, you can now answer the question, what is the lowest value as far as this is concerned, since your problem was actually a direct case. What I want us to do, we start by looking at a direct case where the problem is on maximization. On minimization, sorry, let's start with the minimization problem. And let's refer to the work that I had done earlier on December 2012. December 2012, question number 3, part number B there. I read it through first. Superwings Airways operate 5 different types of aircraft. They are labeled as A, B, C, D up to E. The airways has daily flights to 5 routes, P, Q, R, S, and T, which have variations in terms of the distance, number of passengers, weather conditions, and the airport facilities. The 5 aircraft are not equally adapted to each of the routes. The monthly flight cost. You see now, when the element is above the cost, it hits your mind. This is on minimization. In millions of shillings of each of the aircraft to the 5 routes are given in the table below. And from our paper, you can see the values provided. A good example, if the aircraft A were to take route P, this would cost 10 million. That is the cost to the company. If it were to be assigned to route S, it would cost the company 40 million. But the question is, if you are to keep on now assigning these aircrafts to one and only one route each, remember, what would be our lowest cost? To do this, we are going to use the Hergelian steps. Step number 1, we find out, is our problem balanced or not? There are number of aircrafts to be assigned to the routes defined. We count 5 aircrafts, the same as the number of routes, there are 5. The table given there. Don't change the table. You write down the table exactly the way it is with the figures provided. You are not converting the table. Reason, this is a direct problem on minimization. And we are picking our objective. Remember, the objective is very, very important. I've noted here, this is a minimization problem. Reason, I could hear from the question, the monthly flight cost. And then the question, what is the optimal schedule for us to assign these aircraft to the various routes? And remember, on the basis of one and only one. So from there, because we want to look at the cost, the optimal element must be on minimization, then our problem falls under a minimization assignment problem. Okay? First table, as directly given in the problem. Step number 2, and remember our step 1 is what you're saying, the problem is balanced because number of the aircraft to be assigned are equal to the number of routes defined, okay? The smallest element in each and every column, I've started my case column-wise, but you can still do it low-wise. After all, it doesn't have any impact. My first column has the smallest element here being 6. And in the second column, we have a variable of 12, this one here. The third column, we have a variable of again 12. The fourth column, can peruse through, the smallest here is 30. And lastly, we have a variable of, among these, 32 is the smallest. So what have I done? I've picked each and every column, identified the smallest element in each, and I'm going to subtract that smallest element in each and every column from all the elements in that corresponding column, including itself, up to the point I can now call my new table a reduced column table or matrix. I call it a matrix in that it is having rows and columns. So after I have subtracted the variable of 6 from the first column, and I'm doing this to all the elements including itself, I'll have achieved a 0 somewhere where there was a 6. The same, if I've subtracted the variable of 12 here, I'll have achieved a 0. And I do the same to all the other columns. What have I realized? Immediately I have a reduced column table. There is that particular law which has got no 0 in it. A good example from our table here, I can see in my law 1 here, yeah, look at this class. There's no 0. Look at the second law. We already have a 0 here. But the third law, it doesn't have a 0 in it. The other law has a 0. This one also has a 0. So for the laws that I already have zeros, I've indicated there, there'll be no change. In that, they are not going to change. Even if we were to subtract the 0 being the smallest, after all, there'll be no difference. So don't interfere with those laws that you have already achieved a 0 in it. But for the laws where there are no zeros, identify the smallest element. Here, the smallest will be 3, the first law. And the third law, the smallest here is 1. So what do? We come and convert our table into what we call a reduced law table or matrix by subtracting those smallest elements in the laws where we didn't have some zeros in them. And once we have done so, here we had a 3. After we subtract the 3 throughout, we again achieve a 0 somewhere. And we do the same to law number 3. We have achieved a 0. So you see now, every other law in our table has got a 0. They could even be more than 1 0 in the same law. Yeah, like this one has so many zeros. This one has a 0 in it. So you see all columns, yeah, all the laws in our table here or in our matrix, all of them are having zeros. And once you have achieved those zeros in all the laws, in all the columns, in this table now we are calling the reduced law matrix or table, we now start covering the zeros. You see, I didn't start covering my zeros previously because there were some laws where there were no zeros. So first of all, I achieved zeros in every law that didn't have a 0. So we cover the zeros. How have I done this? I've started by covering the zeros where there are as many as possible. And I could see my fourth law had how many zeros? For all of them. I start drawing a line that can cover as many zeros as possible. Another guide in my case are these zeros, which are on my second column, which were not covered yet. There are 3, all of them. And because I see they fall on the same column, I drew another line covering those zeros. So I've started with these zeros. There were many. The next number of zeros, descending order, remember, are 3. I cover them. But I still find there's this 0 here that is not yet covered, which must be covered, whether it is alone or not. I have closed this particular 0 using a line moving horizontally in my case. We count. How many lines have we drawn covering the zeros? The first one, the second one, only 3. Are 3 lines used to cover the zeros the same as the number of assignments? And the answer is a big no. And as a result of that, we say the number of lines covering the zeros equals to 3, not the same as the number of assignments, okay? Then our solution, if we were to do the assignment at that point, will not actually be optimal. I've indicated here the solution is not optimal in the name of what? Because the number of lines covering the zeros were only 3, not equals to the number of assignments. So if that is the case, what do? We now move to step number 4, where we are saying, can you go back to your table where you have already covered the zeros and you actually identify an uncovered element that is the smallest in the table. So what you do here, you come and identify an uncovered smallest element in the whole table. Where you have closed the zeros, it's where you come back and you identify if there's any uncovered zero or other element which is actually the smallest in the table. And as you can see, perusing through this particular table of ours, we see 1 here being the smallest uncovered element in the whole table. This one here, and they could be like 2 1s or even 3, but that being the smallest, you actually pick that particular value. So what are we going to do with this particular smallest uncovered element in our table? We are going to add that 1 at any point of intersection. For example, here we have a point of intersection between these 2 lines. So this one and this one here, we are going to add that particular 1. So finally, we'll have a 2 and a 2 here. Any value or any element in the table covered by only 1 line will not interfere with it at all. But that which is uncovered, it is not having any line at all, we are going to subtract the 1 from it. And we also do to itself. So 1 here will subtract a 1. A 2 here that is not covered will subtract a 1. And we'll follow that procedure up to a point now we can start again covering the zeros. So my next table, what have I done? My 1 that was the smallest uncovered element, I have subtracted it from any uncovered element in the previous table, and I've also subtracted itself from that particular value, which itself again. Then I have added it to any point of intersection, and I've also not interfered with any element that was covered by just one line. So once we have done so, we will still have zeros in our table, and every column, every row will still be having a 0. What do? We start covering the zeros again. And again, we are starting with the highest number of zeros that can be covered by a particular line. Lowest or column-wise, it doesn't matter. The guide is the descending order as you cover the zeros. What I see in my row 4 here are 4 zeros. So I've covered them using 1 line. Then I still have 3 zeros here. I can come and draw another line vertically. I see this 0 here and this other one in row number 3 won't be covered, so I've covered them using another line. I cannot draw 1 line on each because they are falling on the same column. The better that I draw just 1 line moving column-wise to cover the 2 zeros at the same time. So we count the number of lines covering the zeros. How many are they? 1. This one moving horizontally on row number 4. 2, the one moving vertically on column 2 and on column 1. There are only 3. The 3 lines covering the zeros, the same as the number of assignments. We had 5 assignments. Again, the answer is a big no. What do? We say the solution is not optimal. If we were to do the assignment at this point, we'll still not have achieved our optimal SAGU. Remember, we were asked about the optimal SAGU. How can we minimize the cost of assigning this particular freights when they move to these particular routes? So the solution is not optimal. We do what we call iteration. Iteration means we are repeating the previous stages to a point, and we are able now to say the solution is optimal. We have covered the zeros. The number of lines covering the zeros are only 3, and this does not equate to the number of assignment. So we repeat our previous stage, stage number 4. Stage number 4, we go by again, identify on our previous table here, which is the smallest uncovered element in the whole table. And what I can see in the whole of this table when we peruse through is again this one here. It is the smallest uncovered element. What do we do with it? In this table, we are going to add this one at any point of intersection, like these 2 here, this 0 here are at the point of intersection. We'll be adding that 1 to them. If there's any uncovered element, we subtract 1 from it, including itself, and then we don't interfere with any element that is covered by just one line. And doing the necessary, we arrive at this particular table, which I've shown in this particular document. So when we have the table now achieved and there are some zeros, we ask, how do we close these zeros, or how do we cover the zeros using some